All right, you got okay with this one. Again, these are the equations to solve for.
Emily.
The feature information and everything else. Now, if we just use one observation and we want to find the MLE, then that will be obtained by setting this equation equal to 0. And if you set that equation equal to 0 for the MLE, that's what you get. And then you solve it, you would see that the estimator of each of the PIs would be equal to just XI.
Dr. Longla, can you move your paper a little bit?
What do you mean? Move it where?
I cannot see the lines after MLE.
There's nothing yet. Yeah, that's where I am right now. This is what I'm talking about. So you solve this, and I'm saying when you solve this, what you would get, you would see that the estimate of each of the PIs is XI. Why? Because if you put in XI for each of the PIs inside there, you will see that this cancels. You get 1 minus 1 equals 0. So that's one solution. But then you have a theorem that states that the MLE is unique under certain conditions that this problem satisfies, and therefore you can conclude that it's the only solution. But actually, there is a way to show that it exists and it is the only solution that we have in this problem. But I'm not going to spend time on that. Okay. Thing being here, for example, look here. You have here xi over pi equals 1 minus sum of xi's, sum of xj's over 1 minus sum of pj's, right? This is what you have. But these xi's over pi's, it's all of them actually. This is like saying that x1 over p1 equals x2 over p2 equals, and so on, equals x k minus 1 over xk. So now if you solve these equations and fix, for example, let's say P1 and solve for all of them, solve for P1, P2, P3, P4 in terms of P1 and plug them back into this equation, then you will find that P1 will have to be equal to X1. And then you plug it back into the others and it simplifies that each of the PIs is equal to PI. So you can use this to do that. Okay, and after that, the second part here is about the feature information, which uses the derivatives that we found up there. The information for II, which is negative expected value of the second derivative divided by with respect to pi squared, this is the second derivative that we had, minus, and when you're taking this expected value gets in there, and then expected value of xi is pi. That's why you get 1 over pi, and the expected value of each of them here gets you 1 minus sum of pj's. So you cancel one of that, it remains this. And you know that 1 minus p sum of pj's, I called that at the beginning pk. That's what I called pk. So you take that back in here as 1 over pi plus 1 over pk. So the Fisher information for pi is 1 over pi plus 1 over pk. Then you take for the correlations, you would take I from IH, which would be derivative with respect to I and then derivative with respect to H, which is this derivative. And that's why we take it into the formula to find that the expected value is the negative expected value of negative that, and that the expected value gets in and minus cancel, so you get 1 over 1 minus sum of pj's, which is 1 over pk. So we get that the Fisher information of that represents the correlation is just 1 over pk. And they are all same. This is not depending on IH. So all correlations are same. Therefore, when you finish that, you can write down your Fisher information as the matrix IH, I from 1 through k minus 1, H from 1 through k minus 1. It will give you a matrix that has diagonal elements 1 over pi plus 1 over pk. And the all off diagonal elements are equal to 1 over pk. And this can actually be also written as 1 over pk times J matrix plus the diagonal matrix of 1 over P1, 1 over pk minus 1, where this notation means you take a matrix, you put on the diagonal these numbers, and everywhere else you put 0. And the matrix J is a famous matrix in statistics that takes 1 everywhere. So the one matrix, 1, 1, 1, all entries are 1. Any questions? There is a square here, okay? It's so calm that I don't know if you are actually hearing what I'm saying. Is there any question? Do we move forward?
There's no question from me.
All right, if you are down here, then the next part of that question is what happens with the inverse of that matrix? Technically, the inverse of this matrix, which is necessary, is, I said, AIH matrix, I from 1 through k minus 1, and H from 1 through k minus 1, where AII is equal to Pi times 1 minus Pi. And you would have guessed this because we are dealing with the sum of random variables, and each of the xi's behaves like a Bernoulli random variable. And the variance of a Bernoulli random variable is P times 1 minus P. So this really makes sense based on what we used to do. And then the covariances here would be AIH equals negative Pi times PH. So that's what the inverse of this matrix turns into. And if you want to check that, if you have time to waste, you can prove that this times that equals the identity. Now, how do we get the MLE in this problem if we assume that we have a random sample, IID from multinomial, with P1, P2 all the way to Pk minus 1? Then here I say, hey, if that's the case, then you need to know, and this is what I was trying to develop in class that day, that each of the xi's that is here itself is a vector, because the multinomial always gives you a vector as observation. So each of these is a vector, which says which of them is 1 and the others are zeros. And we take this random sample, therefore we got to write down the likelihood function. And the likelihood function would be the product of the likelihood function that we had up there, just by replacing each of the x's that were there by xi. Now, I didn't waste time writing them again, all of them, but just writing what will happen. When you multiply these things, each of the pj's was raised to the power xij's, and now you are multiplying them, it becomes, the power becomes the sum over all possible i's, because I goes from 1 through n, so becomes, the power becomes xij sum through I. And then the 1 minus sum of pj's was there by itself, raised to the power 1 minus. Now that power is multiplied n times. So that's n times 1 plus 1 plus 1, n times gives you this n. And the rest becomes sum of the sum that was there originally, sum from I from 1 through n. Does that make sense?
Yeah.
And so that's what you get as likelihood function. And here I just wrote that when you have this likelihood function, it implies that pj hat is equal to sum of the xij's over I divided by the sample size n. So if you want to check this, you can check, but I'm not going to take time to go take log likelihood and solve that to get this. So this is what you will get. Any questions? Is there any question at this point?
No.
No.
All right, if you guys have it all, then I can get to the next phase. And I'm afraid we might run into a problem. Strange. The camera ran away by itself. Can I move this now?
Yeah.
The big problem that we have is that my computer is refusing to charge, which means that if it runs out of energy, then the class will automatically stop. And I'm trying to get it to charge, but it's refusing. So, all right. If we are all on the same page, then we continue seeing what's on here. So based on the MLE that we have, we can find the expected value of that MLE, which is sum of expected value of xij over n. But we know that these are independent observations from multinomial. So the expected value of xij is pj. And you're taking the sum over I. So you're adding pj n times. So you get n pj over n. So it's pj. So the expected value equal means that pj hat is unbiased for pj. So pj hat is an unbiased estimator of pj. Then we compute the variance. The variance of pj hat is the sum of variances divided by n squared. Because you have 1 over n, when you compute the variance, that 1 over n becomes 1 over n squared. And the variance of the sum becomes the sum of variances because the variables are independent. And the variance of each of them, it's pj times 1 minus pj, because that's a Bernoulli random variable. And so you're adding n of them, so that is n times pj times 1 minus pj over n squared, and the n cancels. Now you can see that this thing is 1 over n times I of pj. We computed the I of pj, Okay. Am I making sense here?
Yes, Dr. Longa.
Now, again, what I wrote here, I of Pj, this is if Pj was alone. If Pj was the only variable that we were taking care of, then I of Pj would be 1 over Pj times 1 minus Pj, right? But inside this matrix I that I defined here, which is the information matrix here, I of that Pj wouldn't be what I just said there. Am I making sense? This is what it is. But guess what? In the inverse of the matrix, because this is what would bring some confusion there. In the inverse of the matrix, at that position, it's really Pi times 1 minus Pi. So this is what you need to be looking at for deficient information to confirm that you're having the lower bound. So this really means that this estimator of Pj achieves the lower bound, the Fisher, the Rao-Kramer lower bound on that, and therefore P hat J form efficient estimators of the Pj's. So you need to be very careful with this. That's what I wanted to say. Questions? Please give me some seconds to look, see if I can get this thing to charge. Otherwise, we are going to be disconnected from the class. Very rare issue. No idea why today it refuses to work. I never had such an issue. It's not working, not properly. Hopefully this is even better than what we had before. And from that efficiency, we get to this theorem that we had earlier for the multivariate case. And the same theorem holds from the univariate case, the same theorem holds in the multivariate case, with the difference that here, instead of having 1 over I of theta, you have the inverse of the matrix, because you are talking about a vector here. And this justifies what I was trying to explain here to you, that the entry that is here is actually from the matrix here, instead of being from the theta, 1 over what you had in the theta, because it comes from this theorem in here to get there. And same as for the univariate case, the vector theta hat converges in probability to theta. So it is consistent. The P here from the 575 means convergence in probability. The D means convergence in distribution, which means that the distribution of this thing converges to the distribution of that. And this means that the probability that the absolute value of this is larger than epsilon minus theta is larger than epsilon, for any epsilon converges to 0. Okay. If there is no question, then I had this other thing here. So due to this theorem, so by the properties of the normal variable, the multivariate normal variables, we can claim that because this is true, for any variable t equals t1 tp, that's a vector t, square root of n t transpose theta hat minus t transpose t, theta converges in distribution to a normal variable with mean 0 and variance t transpose I minus 1 of theta t. This is a theorem that we had in 575. It's called what's called what? The delta method, or what? How was this called? No, it wasn't the delta method. It is just linear combinations. When we showed that the linear combination of the normal is a norm. And down there, I say, you can use this fact to test hypothesis on linear combinations of theta 1 through theta p. That is that theta 1 through theta p is always what the variable theta is in this class. So the variable theta by definition from the beginning was theta 1, theta p. And that justifies why here you have T1 down to TP, because you need a vector that you can multiply by theta. Are we good on this part?
Yes, Dr. Longo.
All right, then from there, in general, we can take this. We can take, oh, that was for any. We can take any eta, which is a function of theta, and now we want to see the distribution of g of theta hat. If you use a delta method, or you say, oh, because you have the MLE, square root of n for g of theta hat minus g of theta, what would be the distribution of this? This is what we call the delta method in 575. This would converge also to the normal distribution, and the variance shall be the original variance, and then you take the derivative with respect to theta of the function that you have here. Take the multiply on the left and then transpose to multiply on the right. And now the way you put this or transpose depends on what you understand this derivative to be, okay? If you're writing this derivative as a column, then the transpose should be on this side, if this is the column. But if you're writing that derivative here as a row, then the transpose is on this side, right? Because this product should be one number, not a matrix, because we are dealing with G of theta hat, which is just one scalar. Am I making sense? And so here I just rewrote the same thing using eta for G of theta. So if eta is a function of theta with eta hat being G of theta hat, you will have square root of n. This is eta hat minus eta, converges in distribution to normal with mean 0, and the variance is, this is the derivative of eta with respect to theta, I minus 1 of theta, and this is the derivative of eta with respect to theta, transpose. The prime here means transpose. And again, it works as I explained here. If you write this derivative as a column, then it's on this side that you need to transpose. If you write it as a row, then it's that side you need to transpose, because you need to write something that you can multiply. This matrix, you cannot multiply by a row. If you transpose this, you cannot multiply it by a row. So if your derivative, you write it as a row, then you need to transpose to right there to have a column. Am I making sense though? All right, so that's the only issue you can have with these things, knowing where that transpose is going. It depends on how you're writing your vectors, whether your vectors are columns or your vectors are rows. And from this formula, knowing that dealing with the Fisher information, the limit here, when you're dealing with the Fisher information, the limit that you get here, what is it? It is 1 over I of eta, right? the variance in the CLT from the Fisher information is 1 over I of the variable you have, right? That we did that maybe two lectures ago. Square root of n times theta hat minus theta converges to normal 0, 1 over I of theta. We did that, right? And so here I'm changing the parameter from theta to eta, because here this is what my parameter is now. So if this is the parameter, then this variance here has to be, according to what we did before, 1 over I of theta, the Fisher information of eta. Do we agree? Therefore, from that, you can conclude that the Fisher information of I of theta is equal to this, where the -1 here is just 1 over, while the -1 here is the inverse of the matrix. And if theta is just one variable, this just gives you derivative square, right? And that's the formula that I use in that homework there to find the Fisher information of square when you had square root of theta. Now, example of this. We had x1, xn follows IID, normal mu, say theta1, theta2. Last time, our last class, this was the variance and this was theta. What did we find as I of theta1, theta2? What was the Fisher information we found here?
One by theta square, 0, 0, 1 by 2 theta square. Oh, sorry.
No?
Yeah.
Okay.
The
What's that?
shouldn't the upper one be square as well?
That's the square that I don't have it in front of me, and you have the notes there. If you're telling me I'm writing what you're saying.
Yeah, I don't understand. My handwriting is very bad, so I have to redo stuffs again.
I don't see that it's square.
In my
I
own
just
note, there
have-
is no square there.
Yeah, I just have 1 over theta 2.
Theta 2,
Okay.
right? Okay. Because the Fisher information of the mean is the variance. It's 1 over the variance. That is justified, and the variance is theta 2. Now, the reason why I wrote this example again is, now let's say I want to find the Fisher information of theta 1 and square root of theta 2. If I already have this answer, what that theorem says is, if I have those zeros and this is just the Fisher information of theta 2 that is there, and I don't want to bother myself, then I would just compute this thing.
Oh,
As right there. So this is eta. which is square root. So the function is square root. So I'm going to take, according to this formula, square root of 32 derivative. That's 1 over 2 square root of 32, right?
Yeah.
Times whatever you get there, the inverse of this, it's 2 32 squared, right?
Yeah.
And what about this guy? And then power minus 1. So where do we end with this? So when you finish computing that, what do you get this to be equal to?
Theta 2 by 2.
You get 2, 2, 2. It's going to be theta 2 over 2 raised to the power minus 1, which is 2 over theta 2, right?
Yeah.
I'm saying that example. That's what they got in the book that I was saying was different from what we did in class. Yeah, that was 2 over sigma square, right? And theta 2 is sigma square. Is it clear now what I was trying to explain then? So you can have when you take a function of the parameter, it changes the Fisher information through this formula. And this clearly is telling us that if I take square root of n times theta 2 hat minus this is going to converge in distribution to normal 0 theta 2 over 2. So I will not even need to go and waste time trying to figure out what is going to happen. I'll just say, hey, based on this theorem, with this Fisher information that we have here, it is going to converge to normal 0. And then I just take 1 over the variance that is here. Why is that? Because I minus 1, it's very important. I minus 1 is theta 2, 0, 0, theta 2 over 2. And that is what goes here. Are we good?
Just a long run.
So that's it. Is there any questions on this then? This back, so that's where we end with.
Please, can you take that paper back, please?
This is where we end with the Fisher information, and please take this. What's that?
I want to write the last part, so that's why. I'm done. Thank you.
All right, so based on that, we are done on that topic of facial information. And so the next thing is this. And by the way, question to you. Why did I say that we need to invert this and then take this number here to use inside here?
Because in the formula we take inverse of the matrix and not inverse of that particular value.
Because theta hat, that's right, what you're saying, minus theta root n converges in distribution to normal 0, and then here what? What's here?
The matrix inverse, I inverse of theta.
Inverse. Which means this actually means that each of the components, square root of n, theta hat I minus theta I, converges in distribution to normal 0 with sigma square I here equal to I minus 1 of theta, position II. So go to the position II of the inverse matrix and see what the variance is. That's why we had to invert this and then take this to put in there. So the joint distribution is that, but each of them separately has the normal distribution with variance equal to what stands at the position II in the matrix. Are we good? All right. And again, that takes you back to justify again what we had here. Why I call this the efficiency. Well, I said it was efficient because you, in that theorem, you need to invert and take that variance here. All right. So we're done with that. And now what? The last thing on this topic is, what about testing? If we want to test something for multiple variables, not just separate variables as we are used to. So when we have multiple variables, so the test could be a little tricky. We could test that theta belongs to a set omega versus theta not being in that set. And here, our set omega can be defined as J1 of theta equals the A1 all the way down to JQ of theta equals AQ for Q less than P. So we want to test Q equalities with Q less than P, okay? So
I think
I
his
think we
battery is
lost
dead.
Dr. Longlaw.
Yeah.
Class is over. Bye-bye.
All right. Have a good weekend.
And you too.
Bye.
I think we should
Bye.
wait for 5 minutes.
I was gonna wait, yeah.
Oh,
Let's just wait just in case.
we are supposed not to even have class today. I don't know why he wants to have class. Do you understand, Gori?
Do I
Okay.
understand words?
What he's saying? So you have to.
No,
Huh?
no,
Don't tell
no.
me no. You are the one that is explaining now. Don't even tell me no. You are going to
I
explain to me.
understood just the last example. I did not understood all the proof he did. But when he gave example, I just know that he took a formula and he put in that.
Wait, you understand the example? And then you explain to me. You come. I'll come and meet you. You explain.
I will see. I understood what he did in example, but for that, yeah, and because he just took the formula, he inverted the, and he just plugged that in. He did nothing. But before that, whatever he was talking for 30-40 minutes, I did not understand. It was so difficult to read. I was like, what? What's there? What's there? What's there? And by that time, he was on the next, like, he was running away. It was so fast.
And we're
Yeah.
having first test next week.
Yeah. Hey, Tiffany, did you receive the homework 2 scores?
I haven't. Have y'all?
No.
No.
We thought it's just us. Okay, yeah. Yeah.
You guys should have a nice weekend. Go wait. So anything you say is after I've left, you come and tell me. So Stephanie, bye-bye.
Bye.
Uh,
Have a good
I'm
weekend.
I'm not doing anything when we will receive homework. He didn't posted homework 3, right?
I haven't seen it yet, no.
Yeah, I
I
haven't
was
seen
gonna
it.
ask him after class if he had
Yeah,
graded it
same.
and posted.
I think he will post it on Tuesday, but we have test on next Thursday, right?
No,
So
I
he
thought it was
won't
a
be.
week after that.
No,
Hold
it's
on.
on 10th of Feb. So it's like the next Thursday we have test. So I think he should have given by now if he wants it in,
Yeah.
Yeah, let's see. We will ask him on the Tuesday class or we can mail him. Okay. Have a great one. Bye.